Now we're going to take a look at the technical solutions, the process steps in order to achieve the barriers that we need to protect ourselves against microorganisms. So let's have a look at that now. On the last video, we went through what the minimum number of safety barriers would be using the treated sewage water for drinking water production. So let's have a look at what we derived at the previous video. First, we look at bacteria and bacteria removal. And as you see here, the bacteria removal was to be at least minimum 1 million times. This is also true for reduction of viruses, 1 million times. And finally, a reduction of parasites of a minimum of 100,000 times. So, what does this mean in regards to the sewage water, the treated sewage water we calculated in the beginning? How will it look after this minimum reduction? Let's have a look at that now. In the start of the videos, we looked at several literature references in order to estimate a quality of a treated sewage water. Now we're going to look at that quality in regard to the minimum safety barriers or needed minimum reduction based on the MBA. So let's go into this table. Here you see the E. coli, and in the raw water we have estimated about 15,000. We need a minimum reduction of 1 million times or log 6, which after this reduction will give a count of 0.015 of E. coli in 100 milliliters of water. The same reasoning goes for the Clostridium perfringens, the Giardia and the Cryptosporidium, with the exception that for the parasites it's a minimum reduction of 100,000 that is needed. So with this, let's now go to the technical solution in order to stop the bacteria, in order to practically set up these barriers. That we're going to do right now. You have two types of barriers. You have separating barriers and inactivating barriers. Now we are going to start to look at the separating barriers and the examples of technical treatment solutions for those barriers. In this table you will see different types. You have, for example, UF, which is ultrafiltration. And with an ultrafiltration unit, you will need a pore size less than 40 nanometers. If you have an ultrafiltration unit that fulfills those requirements, you know that you can achieve as much as 2.5 log removal for bacteria, 2.0 removal of viruses, and finally 2.5 removal of parasite using a UF unit fulfilling a pore size of 40 nanometers. That will be an example of the separating barriers, and in the table you see different ones, and when you select the treatment step you can go in and get the log removal for the specific treatment method you choose. Now, with that, we'll go to the inactivating barriers to see what they are and what the technical solution for those are. Inactivating barriers. Let's have a look on some of those inactivating barriers in this table. For example, you have hypochlorite, and hypochlorite is very commonly used on the waterworks. And hypochlorite is a chemical, and therefore the conditions in regards to pH, contact time and temperature are critical. So when you talk about hypochlorite and the removal and log removal, it's very important that you specify at which pH, which contact time, and at which temperature. With the optimum pH, contact time, and temperature, you will have with hypochlorite a max removal of log 4 for bacteria, max removal of viruses of log 4, and finally a max log removal of 3 for parasites. With parasite you have to be very careful, because here chlorine hypochlorite is difficult because of the hard shell many times on the parasites. But this is one example of an inactivating barrier like hypochlorite. With this we have looked at the separating and inactivating barriers. Now we'll go in and see what treatment step you can use in order to use treated sewage water as raw water to produce a good and safe drinking water. Now we're going to get into the really interesting part. What processes are we going to use to reach good safety barrier effect? Let's have a look in that in more detail. First, I've chosen ultrafiltration, UF, as my first step. With this we have a reduction of bacteria, viruses, and parasites, of course, particulate material, and also a reduction of the SDI, the silt density index, which is important for the following step, reverse osmosis. I've also made a risk and say that the reduction of the barrier, or the log reduction of the barrier, is decreased with 25%, which is a risk assessment I made for the log reduction. Also, reverse osmosis, following the ultrafiltration step. Here we separate ions and other dissolved pollutants. UF, very good pretreatment, so I've said that the reduction in log barrier is only 10%, so 90% efficiency in regard to the log reduction we're going to look at after this. UV, 400 joules per square meter. Here we have good monitoring, spare parts available, excellent pretreatment, turbidity less than 0.01, and so I assume that 15% as a risk in regard to log reduction. So 85% of the log reduction maximum we're going to use. And final step, hypochlorite, as I discussed. And here in regard to parasite, we'll only say 30% efficient in regard to what I've said before about the parasites and the shell, which could be sometimes hard to break for the hypochlorite and chlorine steps. So, with this, we have 4 treatment steps. And now we're going to look at how they will add up in log barriers in regard to the minimum barriers that we've established before. So let's have a look at the total barrier effect given the risks I put in here in the next slide. We've now chosen some process in order to produce our drinking water. Let's have a look at what those processes will mean for the log reduction effect on the bacteria, viruses and parasites. We have the first UF step, and I've chosen a 25% risk, so the log removal for bacteria will be 1.8, for viruses 1.5, and finally for parasites 1.8, taking in account the risk I've chosen in regard to the efficiency of the method and the water we are going to treat. After that you have the RO, where you have a risk of 10%. With that you have bacterial removal of 2.7, virus removal of 2.7, and finally parasite removal of 2.7 log. So To cut to the chase, what will be the sum of log reduction on bacteria? In this case, it will be 11.7 log reduction. This we shall compare with the minimum reduction we needed based on a raw water of 6. For viruses, it's 9 log compared to 6 log as required by the minimum safety that we did with the raw water before. And finally, parasite log reduction with the treatment process we have, it's 8.9 compared to 5 log with a minimum requirement. So the selected process step will give you this quote-unquote equation of 11.7b plus 9v plus 8.9p. 11.7 log reduction bacteria, 9 log reduction virus, and finally 8.9 log reduction of parasites. Now we're going to summarize this according to the MBA or the P1112 guidelines in Sweden on the next slide. To sum this up according to the Swedish guideline P112 for MBAs, we're going to look at this table. Here you see you have 5 steps. Step 1 is the raw water barriers needed as a minimum requirement, as we started out doing in this video. Then we have step 2, which says raw water source, which basically in some cases you can add some safety if you have some measures taken in the raw water source. But in our case, having treated sewage water, we of course do not have any extra safety here in this step 2 according to the guideline. Step 3, separating barriers. Step 4, the inactivating barriers. And step 5 is the end result of the MBA. And as you see here, when you start out with the minimum requirements in step 1, if you then subtract the barriers you've added, if you end up with a positive answer, that is in step 5 you have a positive number, then you have too few barriers. In our case, as we've seen before, we have good safety in regard to the barriers or number of barriers, technical solutions we have selected. With that, let's go and look at the reduction using the process step that we have selected. So let's go and see what our treatment step will result in for reduction of the microorganism. What are the effects of the ultrafiltration step, the reverse osmosis step, the UV step, and finally the hypochlorite step? Let's have a look at this table, and I will use E. coli as an example on how to arrive at what concentration we could have after these 4 treatment steps in regard to microorganisms. As you see here, E. coli, we estimated 15,000 E. coli in our treated wastewater. And here you have minimum reduction times, which is a huge number. And that is of course equivalent to 10 to the 11.7 log. And here we see the results. Basically, after these 4 steps, the E. coli are non-existent in the water. As you see, they're way, way below 0. Also, you can think on how much water you must drink before you can even find 1 E. coli with this treatment. I have made a little bit of a reasoning here, which you can look at and maybe comment. With that said, we're going to the last slide, which will prepare you for the very important part of seeing how the exact layout of the waterworks will look when we are working with these barriers and treatment processes. Now we have gone through what to do in regards to barrier when you are thinking of using a treated wastewater as a raw water source. The next step, I will take you through the next video, we'll look at the layout of the waterworks, where you have your barriers, and also how the quality of the drinking water in regard to other parameters than microorganisms are sorted out with the treatment process.